All right, welcome to the Explainer. Today, we're going to decode a mathematical object that sits right at the heart of Einstein's relativity. And this thing? It literally describes the geometry of our entire universe.
So this one concept, it's called the metric tensor, and it's just unbelievably powerful. I mean, think about it. It's the reason your phone's GPS knows exactly where you are. It's how we first even dreamed up things like black holes and gravitational waves. And, as if that's not enough, it's the main tool we use to wrap our heads around the expansion of the entire universe. But, when you actually go to look it up, you get these super vague definitions, and then you see this. This beast of a formula, just packed with Greek letters. It looks way more intimidating than it does helpful, right?
Yeah, it doesn't seem intuitive at all. So how are we supposed to make sense of it? Well, what if we could just forget all of this for a second and try to rediscover the whole idea completely from scratch? Okay, let's do it. Let's dive in.
All right, we're going to start with a question that is so simple, I bet you solved a version of it way back in middle school geometry class.
So, take a look. What's the distance between these two houses? On our map here, it's 3 units across and 4 units up. Now, if you dust off your old geometry skills, you'll remember Pythagorean theorem. It tells us the distance is the square root of 3 squared plus 4 squared, which, is 5. 5 units. But 5 units of what? What does that even mean in the real world?
Well, to get a real-world distance, you need something called a metric. And honestly, a metric is just a fancy word for a conversion factor. It's the scale on the map. So if we say 1 grid unit equals 1 kilometer, then boom, the houses are 5 kilometers apart. And at its absolute core, that's all the metric tensor is really doing. It's translating these arbitrary map coordinates into real physical distances.
Okay, but hold on. If it's just a simple conversion factor, why the super complicated name? Why call it a tensor? And why did that formula we saw a minute ago have so many different bits and pieces? There's got to be more to it, right? Well, the answer starts to show up the second we begin messing around with our coordinate system, with our map. Let's see how this whole thing starts to build.
Okay, so imagine we shrink our grid by half. All of a sudden, the coordinate numbers that describe the distance double. Now it's 6 units by 8 units. But did the houses actually move further apart? No, of course not. So to make sure the real distance stays the same, our metric has to change to compensate. Our new metric becomes 1 unit equals half a kilometer. And look at that, the physical reality, 5 kilometers stays exactly the same.
And this right here gets to the absolute heart of what a tensor is. You can think of it like a mathematical machine. Its whole job is to automatically adjust its own parts whenever you change your coordinate system, for one specific reason: to make sure the underlying physical truth, in this case the distance, stays constant. It's what makes sure reality doesn't change just because you decided to draw your map a little differently.
Okay, that totally makes sense for just, shrinking or stretching the whole grid. But what happens if our map isn't a perfect square grid anymore? What if the grid lines are stretched out into rectangles? Or what if they're even skewed at some weird angle?
Well, this is where we had to take Pythagorean theorem and kind of upgrade it. For a simple square grid, the old formula works perfectly. But for a rectangular grid, we suddenly need 2 different scaling factors, one for the x direction and one for the y direction. And if our grid is skewed, whoa, it gets even more complicated. We now have to add in these extra cross terms just to deal with the weird angle between the axes.
So these 4 numbers, the scaling factor for x, the scaling factor for y, and those 2 cross terms for the angle, these are the components of our metric tensor. And we can arrange them all neatly in a little 2x2 grid, or a matrix. It's really just a tidy way to keep all the information about our coordinate system in one place. Okay, so here's the crucial point. This metric tensor thing is an incredibly powerful tool. It lets us calculate distances on any weird, distorted, stretched-out map we can possibly dream up. But why? Why on earth would we ever need to use such a messed-up map in the first place?
The answer is because sometimes the space itself is curved. I mean, think about the surface of the Earth. It's a sphere. It is fundamentally impossible to draw a perfect, flat grid over it where the metric, the scale, is the same everywhere. That is exactly why every flat map of our round world you've ever seen is distorted in some way.
And this is where Einstein made his incredible leap of genius. He realized that this whole mathematical toolkit, which was originally built just for figuring out distances on curved surfaces like our planet, could be applied to something so much bigger, the 4-dimensional fabric of spacetime itself.
Now, in spacetime,
The formula for this distance looks almost exactly like Pythagoras' theorem, but there's one tiny simple change that is just profoundly mind-bending. One of the plus signs flips to a minus sign. So this space-time distance isn't a length you can measure with a ruler. It's actually something called proper time. It's a bit of a strange idea, but stick with me. Imagine you're holding a stopwatch and you travel between two events. The proper time is simply the amount of time that is ticked by on your stopwatch. And here's the really wild part. Just like that 5-kilometer distance between the houses, this value is invariant. That means every single person in the entire universe, no matter how fast they're moving relative to you, will agree on how much time passed on your watch. This right here is the mathematical origin of time dilation.
And just like a flat sheet of paper has a really simple constant metric, a flat, empty space-time also has its own constant metric. We call it the Minkowski metric, named after one of Einstein's old professors.
So here's the thing. If your space-time just looks weird because you're using a wacky coordinate system, you can always do some math and transform it back to that simple, flat Minkowski metric. But what if you can't? What if you're in a part of space-time where the metric is just fundamentally changing from place to place, and no matter what mathematical tricks you pull, you can never make it constant everywhere?
Well, if you can't transform that metric away, it means the curvature isn't some illusion you created by choosing a bad map. No, it means it's a real, intrinsic, undeniable property of space-time itself. And this, my friends, is the grand punchline of general relativity. That intrinsic, unavoidable curvature of space-time is gravity.
Suddenly, the metric tensor becomes the master key to the universe. It is the code for gravity itself. It allows us to calculate the straightest possible paths that objects take through curved spacetime, which to us look like planetary orbits. It lets us compute exactly how much time slows down near a massive body, a correction that your GPS has to make constantly. It tells us where the curvature just goes off the charts, predicting the existence of black holes. It even lets us imagine ripples in spacetime itself, gravitational waves, and a metric that changes over time, which is just another way of describing the expansion of our entire universe.
Think about where we started. A simple rule for right-angled triangles that you learned in school. And just by generalizing it step by step, we built a mathematical tool powerful enough to describe the entire cosmos, from the location of your phone all the way back to the Big Bang. It really makes you wonder, doesn't it? If all of this came from tweaking Pythagoras' theorem, what incredible secrets will the next great generalization unlock?